So we will be solving Chemistry A-Level 9701, Paper 42, May-June 2016. Starting with question 1. Magnesium nitrate is very soluble in water. When a hot saturated solution of magnesium nitrate is cooled, crystals of the hydrate magnesium nitrate and this water of crystallization are formed. In the crystals, 6 water molecules bond to each magnesium 2+ ion, and some of these water molecules are also bonded to the nitrate ions. Suggest the type of bonding that occurs between water and the magnesium ion. So that would be, as you have studied, dative covalent. And between water and this nitrate ion, do not mistake this for any other bonding, but this is hydrogen bonding. Remember what hydrogen bonding actually is. You can think about the example of water to come to this result. Hydrogen bonding is a special type of dipole-dipole attraction between molecules, and it is not a covalent bond. It results from the attractive force between a hydrogen atom covalently bonded to a very electronegative atom, such as oxygen here and nitrogen here, right? And if we take water, there is oxygen only, so you can infer from that. Moving on, describe the arrangement of the water molecules around the magnesium ion. If you look at this, there were 6 molecules of water, so they would give a arrangement of octahedral, right? Okay. Describe in detail what you would observe when crystals of this are heated in a boiling tube, gently at first and then more strongly. Write equations for any reactions that occur. So remember, you have to give an explanation and equations as well. So just remember the step that when this would be heated gently, these water molecules, they will be lost from these crystals, right? So think about it. So you can say the solid dissolves. Why? Let's write the equation first. So this is at when the heating is gentle. This would give magnesium nitrate and 6 molecules of water, right? So what do you see? As you see here, magnesium nitrate is being formed, which is soluble. So you can write a point that solid dissolves. What else you can write? You see that here water is being given off, right? So in what form will it be given off? Obviously condensation is happening. We are going to see water droplets on the tube, so you can say that condensation would be seen on the tube. Remember that you have to write what you observe. So condensation. Other than this, let's write the second equation. What would happen when we are heating this more strongly? So another equation, you have learned this in AS level. It is the decomposition of nitrates, and magnesium oxide will be made with 2 gases. I hope you remember this. Okay, wait, this is NO2. Is it balanced? Yes. So this is the second equation, and here it is very evident that there are 2 gases that are being formed, which give very distinct tests of their presence. For NO2 is a brown colored gas, so you can say that brown fumes will be evolved And you can also say that there will be a gas form which is oxygen that gives a test of relighting a glowing splint. Sorry. So gas formed so this is it for this part. Calculate the percentage loss in mass when this is heated strongly to constant mass. Now what? Okay, so remember that they're talking about when it is heated strongly. So this will happen and this will happen, right? So, and constant, what would the constant mass be in the last? What is remaining in the last? If you go back to your equations, you see that actually magnesium oxide is the one that is remaining in the last, right? So the constant mass would be of magnesium oxide, and the initial mass that you are going to take to find out the percentage is going to be of this, right? So what you do is you simply take out the MR of MgNO3 taken twice dot 6H2O, which would be, if you calculate, it would be 256.3, and then you take out the MR of MgO, which is 40.3. Let's just see what is the percentage of this in this, right? So percentage 40.3 over 256.3 into 100, and it gives, it's 15.7237. This is it. Now remember that this is not the final answer, this is just the percentage of mass that is remaining. Yes, because it is from the mass of this magnesium oxide which would remain. Now you need to simply subtract it from 100 to find out the percentage loss in mass. Just this, and that would give us 84.3. Question 1 part B. Explain why the group 2 nitrates become more stable to heat down the group. So down the group, the cationic radius, or you can even say cationic size, increases down the group. Hence it becomes difficult for them to polarize the anion, which is the nitrate in this case, or you can say it becomes harder to distort the nitrate ion. So, or you can even say polarizing power decreases down the group. So just for 2 marks, these 2 points should be present. This is very easy, you have to memorize this. So cationic radius increases down the group, hence less polarization or distortion of nitrate ion. Also, don't just say that of the anion, because we know that here nitrates are being talked about, so please write nitrate ion rather than anion. Magnesium nitrate and silver nitrate decompose on heating to produce the same gases, meaning that would be NO2 and oxygen. So silver nitrate also produces silver metal during decomposition. Write an equation for the decomposition of AgNO3. This is easy. Just write AgNO3 and write all the things they have said. They said that it produces Ag metal, and it produces the same gases as when magnesium nitrate decomposes. So NO2 and oxygen. Right? Now simply try to balance the equation. Since oxygen here are 4 and here are 3, let me just write down 2 over here because I wrote 2 here, I wrote 2 there, and then for Ag2, and that's our balanced equation. Question number 2, ethanoic acid is a weak acid. Explain what is meant by the term weak acid. Weak acid is the acid that partially ionizes. The pKa values for 4 acids are listed below. State the mathematical relationship between pKa and the acid dissociation constant. This comes a lot in the exam, so make sure you have memorized it. Okay. With reference to acidity, explain the difference in pKa values between acid 1 and acid 2. Okay, so acid 1 and acid 2. For acid 1, the pKa value is smaller, which means that Ka value for acid 1 would be higher. If you do not know this, just write down random values in your calculator and then check that if you put a small value for Ka in this mathematical formula here, if you put small value for Ka, then the value for pKa would be greater. And if you put a bigger value for Ka, then the pKa value would be smaller. So which means that here the pKa value for acid A is smaller, which means it must have a higher Ka value. That also means that Ka is the acid dissociation constant, so it means that acid A is more acidic than acid 1 is more acidic than acid 2. And why is there? So acid 1, which is actually ethanoic acid, it is more acidic than acid 2, which is the propanoic acid. Because acid 1 has less alkyl groups and acid 2 has more alkyl groups, and alkyl groups are electron donating groups, and if they're in large number they are going to make the OH bond stronger, due to which the H plus won't be available as much and the acid would be weaker, because H plus contribute to the acidity, right? So acid 2 and acid 3. Acid 2 and acid 3, the difference between them is that acid 2 doesn't have chlorine and acid 3 has chlorine here. And let's look at the pKa value. pKa value for acid 3 is lesser than acid 2, and as I told you, if the pKa value is lesser, then that means that Ka value is higher, and if the Ka value is higher, the acid is much more acidic than the other acid. So also acid 3 is 2-chloropropanoic acid. So if you write the name, that's good. I'm not writing it right now. So acid 3 and you have to give the reason. If you notice that there is chlorine in 3, and chlorine is a electronegative atom, due to which the OH bond is weakened, and there is a more presence of H plus ions, and that increases the acidity. So you can write the reason as due to the presence of electronegative chlorine atom. Acid 3 and acid 4. There's just difference in the distance of chlorine from the CO2 minus group, and the pK value for acid 3 is lesser, meaning Ka value is higher, Again, acid 3 is more acidic than acid 4. Acid 3 is more. And this is because the chlorine atom is closer to CO2 minus group. So that would make the OH point weaker. Draw a fully labeled diagram of the equipment needed to measure the voltage of an electrochemical cell consisting of the standard hydrogen electrode and the standard CuC2 plus electrode. This is the platinum electrode for the standard hydrogen electrode. The other one would be the copper electrode, because it is present in its metal form, in its solid form. Right, this is the voltmeter, and it is very important to show the voltmeter and the salt bridge. And you have to label too. You have to show where the hydrogen gas would enter. You have to show that this is the platinum electrode. Actually, you should use straight lines too. It's just this show arrow and this. These use a ruler. Platinum and bit. Here should be hydrogen ions, aqueous form. Here should be copper ions, aqueous, and this is copper. And that is it for the diagram. For the cell drawn in part 1, calculate the E cell and state which electrode is positive. So E cell has a formula. E forward minus E backwards. Now if you see from your data booklet, for copper's equation, the electrode potential is positive, let me write down, positive 0.3.4, right? And we know for hydrogen it is just 0. Right, so that would simply give us 0.34. Also forward would be this and backward would be this, obviously, because forward is the one that has a more positive electrode potential, so that would be copper. So the answer would simply be plus 0.34. It is important to give the sign in A cell. Identify the positive electrode. The positive electrode would be of copper, because at the copper's electrode, reduction would be taking place, and reduction is the gain of electrons. So that would be right. Now part D, a monobasic acid has a Ka. Okay, so the K is given. Calculate the pH of a this much concentration solution of D. Okay, so for finding out pH, you need the concentration of H plus ions, right? Now to explain you, I'm just taking a random example of any monobasic acid. So I'm just taking the example of ethanoic acid, right? So let me write down its equation, dissociation equation. Right, and that we know that Ka would be now. If you see that we have been given the concentration, right, and know that this concentration is actually of this. Remember that this is an example. So using Ka and using this given concentration, we can find out the H plus concentration. Now what are we assuming here? That very less acid has been dissociated, so this concentration is actually the same of this, and these two, since they are going to have actually the same concentration as the equation shows, right? So what you can write is just Ka into 0.1 is equals to H plus square. Okay, now write down the value of Ka, and you are going to get the concentration of H plus as 1.11 10 to the power minus 3. This is the concentration of H plus ions, and you can use this equation to find out the pH. After using the equation, you are going to get an answer of 2.96, and you can write 3.0 because we write pH to one decimal place. An electrochemical cell similar to the one you have drawn in part C1 was set up using this much of concentration of solution of D in the hydrogen electrode instead of the standard solution. Standard solution's concentration is just 1 mole per dm cube. So use the data and the Nernst equation, this, remember you have to use this one which has been given, to calculate the new E cell in this experiment. Okay, so we have to find out this E right here, this, okay, and this is the electrode potential in the standard conditions, and that would be 0, because we know that for hydrogen the standard electron potential is 0. So 0 plus 0.059. Now how do we find out this H plus concentration? Do not mistake that this is actually H plus concentration. No, it's not. You have to find it out. If you go back to see that they have written that Ka is given in this part D, and it is a part of D, right? So again you use Ka to find out the H plus concentration. Now we had already done that, and this was here because this is 0.1. we had done this whole procedure here of finding out H plus concentration, and that was 1.1 10 to the power minus 3. So we can write down directly. So log 1.11 10 to the power minus 3, that would give us oh, minus 0.17 for what? Volt. Now, again, here is the part where many of you mistakenly think that this is the final answer for the E cell. Remember that this and this, they are not the same. This is E cell, this is the new electrode potential. So for E cell, again, we know the formula: E potential forward minus backwards, and to find that out, it would be plus 0.34, that was of copper, minus 0.147, that would give us an answer of plus 0.51 volts. Question number 3. 2-bromopropane can be used to synthesize methyl ethylamine and 2-methylpropylamine. Okay, draw the structure of the intermediate X in the box above. Okay, so just this is from the AS level syllabus. What is happening here is that okay, this is the haloalkane, which would have definitely converted to nitrile here in this reaction, and then it would have definitely reduced to this amine. So definitely nitrile would be forming here in this intermediate. So what would be the structure? It would simply be CH3. These are CH3, right? And there are two CH3, CH3, and then this, what is this? It's actually CH. Then we have a Br, but we need to remove the Br and attach the Cn to it. So Cn. So this is the intermediate, and then let's go to part 2. Suggest reagents and conditions for reaction 1. So reaction 1, this is whole AS level stuff. What is happening is that it is a reaction with ethanolic ammonia, which is done under high pressure, and heat is also required. So the reagent would be ethanolic okay. Now reaction 2, as we saw that this is a nitrile is being added, so definitely ethanolic KCN or NaCN, and definitely heat under reflux is the condition. So remember to write ethanolic and heat under reflux. Reaction 3, this is reduction of the nitrile, and obviously for reduction you need a reducing agent, and reducing agent could either be H2 and nickel catalyst, or it could be LiAlH4. So H2 and nickel catalyst, or do not write both, just write one. Write an equation showing why aqueous solutions of ethylamine are alkaline. Now what are alkalis? Alkalis are bases, and bases, what do? They are proton acceptors. So you must show that ethylamine accepts a proton. That would give the evidence of its aqueous solutions being alkaline. And also aqueous solution, since they have written, so you have to show the reaction with water. So just write the formula. So that would be CH3, CH2, NH2, right, in water, and it needs to accept a proton. CH3, CH2, NH3 plus. Don't forget to show the plus. Plus, and what would be formed? OH minus, because one hydrogen was taken from water. Alright, and also alkaline means these hydroxides should be present, right? That's what contributes to the alkaline condition. Compare the basicities of ethylamine and ammonia. Explain your answer. Simply, ethyl is more basic than ammonia. And why is that? Because of the electron donating alkyl group in ethylamine, ammonia doesn't have them. And what will they do? They will make the lone pair on nitrogen more available for accepting a proton. That's what will make ethylamine more basic, because of the presence of electron donating alkyl groups, which make the presence of lone pair of electrons on nitrogen more available to accept a proton. Part C. Solutions containing mixtures of amines and their salts are buffer solutions. Explain what is meant by the term buffer solution. Okay, so buffer solution is a solution which resists a solution which resists changes in its pH when small amount of H plus write two equations to show how a solution containing a mixture of this and this, okay, so amine and its salts, acts as a buffer. Since we said that they resist the change in pH when H plus and OH plus are added, so we need to show that. Let's write down the equation for this amine first. It will obviously accept a proton. We did that in the earlier part as well. H plus, that was simply give CH3 and H3 plus. Don't forget the plus. CH3 and H3Cl. We have to show it with the hydroxide. And what can it give? Actually, it should, now since here it was acting as a base, here it should act as an acid. So it should give a proton NH2 plus H2O plus Cl. Okay, question number 4. There are two isomeric complexes with the formula this, one of which is an anti-cancer drug. Draw diagrams to show the three-dimensional structures of the two isomers. Okay, so obviously this will show the geometrical isomerism, which is cistrons. So just draw it in the square planar shape. So first we will show Cl or NH3 on the same side, and the other one would, this is cis and the other one is trans. Cl here, NH3. Okay. Comment on the polarity of the two isomers. Okay, explain your answer. So this is a 1 mark, so you need to write just one sentence. That maybe you can say that this cis one, cis trans, this cis one is more polar because the chlorine is on the same side. So cis is more polar. Both partial negative chlorine being on the same side. And you can even write that in trans, the partial negative chlorine are at 180-degree angle to each other, so they cancel out the bond dipoles. So trans is non-polar. Oxaloplatin is another successful anti-cancer drug in which the stereochemistry around the platinum atom is the same as that in this. Okay, explain why there are no isomers of oxalo. If you look at its structure, you can tell that it can only exist in the cis form. So maybe because of the difficulty for the NH2 and O to change places, this is like impossible. They cannot change places, so trans cannot be formed. So you can say that only one structure of the complex is known. Okay, and this is the monodentate ligand. What does this indicate about the stereochemistry around the nickel atom? Okay, since they have told you that only one structure of this complex exists or maybe is known, so if there would, it definitely has to be tetrahedral, because if it was square planar, then it would have shown cistrons, and cistrons would result in it having two structures of this complex. So it means that it is tetrahedral. Draw a three-dimensional diagram showing the structure of this complex. Okay, since it's tetrahedral, it would be something like this. Cadmium ions form complexes with primary amines and with 1,2 aminoethane. Okay, so this is shown. Write an expression for the stability constant case tab for equilibrium 1 and state its units. Okay, so this would become and this 4 right here will become its power. Okay, now how do you find the units? Simply write mole per dm cube divided by, is this mole per dm cube, this mole per dm cube, and this with the power this. This cancels out, and what will this become? Remember that it is 1 over mole per dm cube into the power 4, so that would become mole minus 4 dm cube. 3 4 is 12 and positive 12. Okay, cadmium ions are poisonous and need to be removed from some water supplies. This is often done by adding a complexing agent. In a sample of groundwater, the concentration of cadmium ions is this. Okay, calculate the concentration of this needed to reduce the concentration of cadmium ions in this dilute solution by a factor of 1000. Okay, this is very easy. You just write the equation from the above part, which is this one. Obviously, because you can see here that this was stated in the question, and you can see the cadmium ions being reacted with this. Okay, so let's copy the equation. Okay, so let's write initially what the concentration of each of these three is. So at start cadmium ions concentration is 1 to the power minus 4, right? And this is obviously not known for now, so let me just write it as x, and then this is obviously 0 because it is the start of the reaction, so none of it has been formed, this complex. Then at equilibrium, since this reaction is reversible, that's why equilibrium is established. Equilibrium, we need to divide this initial concentration of cadmium ions by 1000. Okay, so 1 into 10 to the power minus 4 divided by 1000 is actually 1 into 10 to the power minus 7. Okay, so this is the equilibrium at concentration at equilibrium, and this is x. We don't know this, and this would be what? We would actually subtract 1 into 10 to the power minus 7 from 1 into 10 to the power minus 4, because there is 1:1 ratio between cadmium ions and this complex. So if these many are remaining at equilibrium, so we should subtract this from this to know how many have been given to this, to know its concentration. Okay, so that's how it's done. And now we will get this as (9.99 into 10 to the power minus 5 mole per dm cube). Now what we need to use to find out the is this case tab equation. Okay, and case tab has been given to us here. Okay, so let's not rewrite the equation. 3.6 into 10 to the power 6 is our case tab. 3.6 into 10 to the power 6 equals to this concentration, which is 9.99 to 10 to the power minus 5 over cadmium ions concentration at equilibrium, it would be 10 to the power minus 7 into x to the power 4. Please remember this. And this would become concentration of this would finally be 0.129. Okay. Values for enthalpy change and Gibbs free energy for equilibria 1 and 2, and the values for entropy change for equilibrium 1 are given in the table below. All values are at a temperature of 298 Kelvin. Alright, suggest a reason why the enthalpy change values for the two equilibria are very similar. Okay, so whenever you think about the enthalpy change, it must be related to the bonds, type of bonds being broken and formed. So if you see here that in these equations, the same type of bonds are being formed. If you see this, you can say that each complex is formed by making 4 nitrogen cadmium bonds. How? Because if you see here, there are 4 of these monodentate ligands. 4, right? So 1 nitrogen in each ligand and 4 nitrogen cadmium bond. And if you see this one, the other equation, here you can see this is a bidentate ligand. There are 2 nitrogen in one ligand and there are 2 ligands, right? So you can see that by making 4 nitrogen cadmium bonds, right? And obviously, since the cadmium ions were dissolved in water, right? So it must have been like this. Six water molecules, right? So you can say that breaking of 6 oxygen cadmium bonds. Alright, calculate the entropy change for equilibrium 2. Okay, so right, so we have the equation. Simply using this, we put in the values. Remember that this would give us answer in 0.01409, and then we need to multiply it by 1000 to get it this unit, right? Joules per Kelvin per mole. So that would become 14.1. Suggest a reason for the difference between the entropy change you have calculated for equilibrium 2 and that for equilibrium 1 given in the table. Right. So it's simply, if you see in the table, entropy change for equilibrium 1 is much more negative than what we calculated for equilibrium 2. And why is that? There must have been decrease in entropy for equilibrium 1. That's why the answer is more negative. So let's see. If you see here in equilibrium 1's equation, there are 5 moles of 1 here and 4 here, 5 moles of solutes being used to make this, right? Make 1 mole of something, make 1 mole of this complex. But in the second equation, you can see 1, 2, 3 moles of solutes being used to make 1 mole of. So equilibrium 2, you can say in this way that fewer moles of solutes are forming 1 mole of the complex, so less there is less uh, decrease in disorder, or you can say less loss of disorder for equilibrium 2. Okay, so less loss of disorder. Which of the two complexes is more stable? Give a reason for your answer. This is easy because here both the K stab values are given for the equilibriums. K stab value for equilibrium 2 is higher, which means this complex is more stable. Is more stable due to higher K stab value. Esterases are enzymes that hydrolyze esters. Enzymes can be quite specific in the structures of the substrates they act upon. For example, an esterase is isolated from the mold, will hydrolyze phenylethanoate but not its isomer methylbenzoate. Outline how enzymes catalyze reactions and explain their specificity. Use diagrams in your answers where appropriate. Okay, so let's first write down, then we can draw the diagram. The most essential point that you need to write when it comes to enzymes is that the substrate has a complementary, has a shape After writing this point, you can say that substrate binds to the active site, because you need to explain how they catalyze reactions. Forming an enzyme substrate complex, right? And then you can say that also, yes, you can say that interaction with site causes a specific bond to be weakened, which breaks. Then you can say then the products are released from the active sites. For a diagram, you can draw any appropriate diagram, but make sure that it is labeled. This is our enzyme, right? And then draw the substrate. Make sure the labeling lines are straight. And this is our substrate. Next step would be to show them binding. Let me draw it with another color. And then show that the products are released. Okay. Sample bottles of each of the isomers phenylethanoate and methyl benzoate have lost their labels and so have been named isomer A and isomer B. The carbon 13 NMR spectra of isomer A and B contain the following peaks. The identity of the compound responsible for each spectrum can be deduced by studying the chemical shifts of the peak in the spectra. Okay. Use the data booklet to assign the correct peaks to the labeled carbon atoms in the structures of the isomers below. Write each value next to the relevant carbon atom and hence deduce the identity of each isomer. Okay. Let's look at this carbon atom first. Okay, so this is next to this, right? And if we see that, how do you read it? First of all, see that this carbon atom is sp3 hybridized, right? It is sp3 hybridized and it is next to a carbonyl group, right? Carbonyl is this one, right? So let me write down points for it. Now you can very easily read off the peak from your data booklet for this, and you can find out that its range is actually from 25 to 50, and this is very distinct in this table. There's no peak smaller than 50 than this one, other than this one. So it's going to be 26. Okay, so now for this one, let me erase this. Now for this carbon, first of all, it is sp2 hybridized. Okay, it is sp2 hybridized, and so if we write about this, sp2 and also carboxyl. Now read off the range that is given in the data booklet for sp2 and carboxyl. It is 160 to 185. Now look at this table. We already know it's P, but let's look. 162, definitely this one. 169. Now so this is B. Let's look at this carbon. It is sp3 hybridized and next to oxygen. For 52 70 is the range, and it's this 52. Okay, and then we look at this carbon. Again, I think it's sp2 hybridized and it's the same range, which is 160 to 185 for sp2 carboxyl. So that would be 167. That's it. These two isomers are difficult to distinguish chemically. Describe a method of converting them to suitable products in step 1, which can then be tested in step 2. You should state the regions and conditions for each step and any observations you would make. So first of all, the first step, since they're both esters, they both have ester groups, so the first step would be to break them, right? And different products would be formed, which would allow us to further see what to use in order to distinguish them. So let's write that down first. And how can we break the ester bond? You have to heat it in the acidic medium to hydrolyze the ester. So heat. Now let's see what the products would be. Here, if you break this bond, a phenol would be formed and ethanoic acid would be formed. Okay, and for this, if you break, then benzoic acid would be formed, and the other is methanol. So if you remember, you studied the test for phenol with bromine, aqueous bromine, so we can use that because no other product would give any reaction with bromine, aqueous bromine. So we if when we add aqueous bromine, then what would happen with B is that it has phenol, right? So it would decolorize, or you can say it would give white PPD because of phenol. Question number 7. Amino acids can be separated by electrophoresis. Draw a labeled diagram of the apparatus used to separate a mixture by electrophoresis. Okay. So let's draw the diagram. First of all, let's draw a DC power supply. It is very important to show the DC power supply. And it is very important to show the positive and the negative of the power supply. And then it is very important to show that the circuit is complete. Okay, so I've shown the amino acid mixture placed here, and then I've showed the glass slide and the filter paper soaked in buffer solution, and the circuit is complete because these wires are going in, and the electrolyte positive, negative. Okay. Explain the principles of the separation of amino acids by electrophoresis. So that's direction is obviously dependent upon the charge of the amino acid, whether it will be attracted to the negative or the positive side. So direction. And then you can say that distance traveled depends on the MR of amino acids. Saying mass is not enough, you have to say that the MR. Electrophoresis is usually carried out in a buffer solution. Give 3 buffers with pH values of these. Given 3, okay. Suggest with the reason which buffer would be most suitable for the separation of the following, okay, amino acid mixtures. Your reason should refer to the structure of each molecule. The structure of these amino acids given. By structure they mean you should give the reasons by looking at these side chains of these amino acids. So first of all, aspartic acid and valine. So let's look at their side chains. Side chain of aspartic acid is this. Okay, so and valines is CH3. Okay, The buffer pH most suitable for this mixture of amino acid would be 12, right? Why 12? Because aspartic acid would give its hydrogen to the hydroxide present because the pH is 12, right? And then it would gain a negative charge, and then it would be attracted towards the um, positive electrode, and it will move further than valine because valine is neutral. So yeah, that's why the pH would be 12, and you have to give the reason because will be CH2COO minus, hence moves further to positive electrode. Remember, you need to separate these, so as far apart they are from each other, the better. Positive electrode, then valine. For these, we have lysine and serine. So lysine side chain, it's quite long, it's H2N, and then we have CH4 CH2, and for serine it's HOCH2. What will happen to these? This has an amine, while this has an aldehyde. Actually, not aldehyde. You can say that the buffer pH should be 2 because with this amine it can accept a proton, right? And if it will accept a proton, it will get a positive charge and it will be attracted to the negative electrode. Tyrosine, the side chain is okay. And for phenylalanine, it is CH2. So again, if you see this H could be donated, so buffer pH should be 12, so there would be hydroxide which would accept this and would make with negative charge CH2. Moves further towards electrode. Part C. Draw the structure of the dipeptide glycine and serine, showing the peptide bond in full. Okay, so H2N. First of all, always if the glycine is in the start, you have to show glycine first. Side chain is just an H. And then serines R chain, R group is CH2 OH, K, and here H, COOH. The infrared spectrum of glycine serine is shown below. Okay, use the data booklet to identify the bond in the molecule of this dipeptide that is responsible for each of the peaks indicated on the above. Okay, spectrum. G, for G, it is somewhere. So in the data booklet, there is a peak for 1040 till 1300, and that's for alcohols, ethers, esters. Okay, so that is what G is. Okay, let's look at F. It is somewhere between 1650, I guess, and that's okay, so that's definitely that's for also to go back to your structure for the dipeptide. There is a carbon oxygen bond, yes, and it is over here. Okay, and we also got there are many, and for E, 3300. Okay, that's okay. It could be OH or NH because NH range is 3300 to 3500, and OH is quite a lot. So, and both of them are present in this structure, NH, OH. So you can write either of them. Okay, so question number 8. Describe and explain the trend in the solubility of the hydroxides down group 2. Okay, so solubility of enthalpy change of lattice actually decreases more significantly than enthalpy change of hydration, and enthalpy change of solution actually depends on these two, right? So hence, according to this formula, enthalpy change of solution enthalpy change of solution is equals to minus enthalpy change of hydration plus enthalpy change of lattice. Enthalpy change of solution becomes more exothermic, and more exothermic enthalpy change of solution becomes, meaning solubility increases. Part B, calcium reacts rigorously with HCl producing H2 gas. How would you expect the enthalpy change for this reaction to compare with the enthalpy change for the reaction where an HNO3 is used in place of HCl, but all other conditions are the same? Explain your answer. Okay, so enthalpy change would be the same for both of the reactions because both HNO3 and HCl are strong acids, so they fully ionize. The ionic equation for this reaction is shown. Construct a fully labeled Hazz's law cycle to connect each side of this equation to the relevant gas phase ions. Use your cycle the following data and data from the data booklet to calculate a value for X. Okay, so let's make a Hazz's cycle. Firstly, let's write this equation here. Calcium solid Now let's take stuff step by step. Let's look at this calcium in solid form first. What do you need to convert it into so that you can convert it into that, from this to this? So firstly, what you need to do is convert it into its gaseous atom, right? So let's do that first. So enthalpy change of atomization of calcium is given, I presume. Yes, it's given. So as soon as you make the arrow, write the enthalpy change so that you are not confused later on with all the arrows. 178. Okay, now what we do is that, what do you think you need to do? Now we need to write down its ionization energy to convert it into a calcium 2 plus gaseous, right? So let's do that. First plus gas, here will come the first ionization energy, which is 590 from data booklet. Now the second ionization energy, 2 plus gaseous. This is very important to write the states. Second ionization energy is 1150. And now what is this? The third arrow. This would be finally our enthalpy change of hydration, and that is given in the table. Minus 1576 minus 1576. Okay, so the calcium stuff is done. Now let's look at our hydrogen. How to convert hydrogen from this to this? Okay, so for that, firstly we need to break the bond between these two hydrogen atoms. So for that, we need to see the bond energy from the data booklet. So and it would become 2H gas, and the bond energy, that would be 436. Okay, so, and don't forget to write this 2. Alright, then we have what? Okay, so there is this plus missing here and from here, this plus. So for that we need the first ionization energy of hydrogen, right? So I'm going to make it over here. First ionization of energy, it would be converted to 2H plus gas. Okay, and the first ionization of energy is 1310. Okay, and then lastly we have to convert this to this, and that is hydration. The percentage of hydration, which is given as negative 1090. Now we need to take notice of one more thing, and that is, if you see that there is a 2 here, a 2 here, a 2 here, right? So what you need to do is, you need to multiply this by 2, because you see that there are 2. Okay, so first ionization energy for 2 hydrogen atoms, so you multiply by 2, you multiply this by 2, and you multiply this by 2 as well. Okay, now this is done. Now how do we make the equation? What we do is, we simply make this clockwise circle in the middle, right? And then we see that whichever arrow is going in the same direction as this clockwise circle, we write it on one side of the equation, and whichever is going in the opposite direction to the circle, we write it on the other side of the equation. So let's see. First of all, see this and this. So let's make the equation. Now let's see for these ones first. So they are all going in the opposite direction, so let's write that down. Actually, let's write down those first which are going in the same direction. So we have this, okay, and we also have these, okay, this too, right? So let's write that down. Plus 4 plus 2 into negative 1310 and plus 2 into negative 1090. Now comes the other side of the equation. So these are going in the opposite direction. This is also going in opposite direction. So now our equation is made. Let's check if we have written everything. So we have written 178. This is done too. This is done. This is done. This is done. This is done. Done. Okay. And now if you simplify the equation and find out the answer, and it would be negative 534. Moving on. The standard enthalpy change for the reaction between calcium and ethanoic acid is less negative than X by 2 kilojoules per mole. Suggest an explanation for this. I know that ethanoic acid is a weaker acid, so it incompletely ionizes. So the enthalpy change of ionization of ethanoic acid must be 2 kilojoules per mole. Energy is needed to ionize it. So enthalpy change of ionization of must be the anti-inflammatory drug can be synthesized from benzene via the following 6 steps. Okay. Draw the circles around any chiral carbon atoms in the above 5 formulae. There are no chiral carbons in this benzene. Let's look at this. there are no chiral carbons here as well. This is a chiral carbon. Okay, and here there are no chiral carbons. This is a chiral carbon. Okay, suggest the structures of compound H and J, draw them in the boxes above. Okay, so you see that there is this additional thing after step 3. So what could have been added to H to give us this? So one thing that I can think about is there must have been a ketone, because in AS level you must have studied about the nucleophilic addition reactions of a ketone, where we use the reagent HCN and catalyst NaCN, and what happens is that the carbon double bonded to oxygen changes to carbon bonded to hydroxyl and nitrile groups. So that is exactly what is seen here, so it should be and that is how, if these two bonds are broken with this one bond is broken, and then CN attaches and H attaches to O, so that would make hydroxyl. Okay, and for J, what is being done? How do we convert this to this? Okay, so if you notice here, this is the carbon-carbon double bond. So how can we make carbon-carbon double bond? Actually, the dehydration of alcohol does generate alkene. It is done by heating the alcohol in the presence of a strong acid like H2SO4. So definitely it would be like this. Here I forgot to make a ring, so don't forget that. Again, a ring in the benzene. Okay, so J is done. And if you're wondering, there is another way to make J. You can do any of these steps. Either you make the double bond with a CN, or you just make a carboxyl in the place of CN and make the remaining molecule as it is with OH and this CH3. So it's up to you. Let me make it here. And from AS you learned about the hydrolysis of CN, which converts it into carboxyl. So I hope you remember that. So either you can make this or this. Moving on, suggest reagents and conditions for step 1 to 6. Okay, so in step 1, what is happening? Benzene is being converted. Okay, so definitely alkylation has taken place here. So for alkylation, you need to have the alkyl halide as a reagent. This, from where this comes from. Okay, so let's see what the alkyl halide would be. So it has 1, 2, 3, 4 carbons. Okay, and let's write the formula for it. It would be CH3 2, because there are 2 CH3, these and this, and then there is CH. Okay, there's CH, and then there's CH, and then there's CH2 Cl. Okay, so CH2 and Cl gets removed when it attaches itself in the place of hydrogen if benzene ring. So that is one reagent, and we need our AlCl3 plus, don't forget, heat. Now step 2. What is happening in step 2? Okay, this is definitely acylation. Let me write down it. Okay, now again for acylation you need the acyl, and it would be what? It would simply be CH3 and COCl, and that Cl would get removed and this would come. So CH3 COCl plus AlCl3 again plus heat. Step 3. What is happening in step 3? You see, as I explained earlier, definitely this is the nucleophilic addition of carbonyl. Okay, so what were the conditions? I said that we needed a reagent, HCN, and catalyst, HCN plus catalyst, NaCN. That is it. Basically, NaCN would give the CN and HCN would give the H. Okay, I can write down the reaction for you. This is nucleophilic addition. Then we have step 4. What is happening in step 4? Definitely dehydration of alcohol. And reagent, as I told you earlier, is a very strong acid, like H2SO4, and it should be concentrated and heat should be provided. So concentrated H2SO4 plus heat. Okay, now for step 5, CN is being converted to CO2H, and this is hydrolysis of nitrile. So we need water and we need acidic medium, right? So we can say aqueous HCl plus heat. Let me write down the name of the reaction first. Hydrolysis and aqueous is very important to write. HCl plus heat. Okay, lastly step 6. This is simply reduction of alkene. So the catalyst should be the reducing agent, you can say H2 plus. Please don't write LiAl H4 here, because here this is required, plus heat. That's it. Now part D, name the mechanism of step 1 and state the type of reaction for step 6. Okay, so the mechanism would be definitely electrophilic substitution, because in this we are using alkyl chain as an electrophile with a positive sign, and that's why it is, and we are substituting a hydrogen of benzene with this alkyl chain, so that's why it's electrophilic substitution. And the type of reaction for step 6 is reduction, as we wrote down before. You can even say hydrogenation or addition. Question 10. Complete the electronic configuration of the iron atom. Okay, so iron's atomic number is 26, so 3s2, 3p6, 4s2, 3d6. In some of its complexes, the Fe3 plus ion has only one unpaired electron in its d orbitals. Using symbols to represent electrons of opposite spins, complete the following diagram to show the d orbital electronic configuration of this Fe3 plus ion. Okay, so Fe3 plus ion must have 3 less electrons than this configuration. So we know that since 4s is the orbital that is filled first, so electrons would be removed from it first. So 2 from here, 1 from here, and then there are 5 electrons left in 3d orbital. So how can we make this? We'll start filling from lower energy first. First this. Three, 4, 5. A solution containing a mixture of so for electropotential values of 10 tens ions, and for irons since the electrode potential of irons is greater, so E cell would become 0.777 minus 0.15, and it would be positive 0.62. Now what reaction might take place? So since the electrode potential of iron Fe3 plus and Fe2 plus is greater, so they will undergo reduction, and hence we will say that you can say that Sn2 plus will reduce Fe3 plus, right? You can say do this according to the equation, because the backward reaction for 10 will take place. So reduce and make Fe3 plus to Fe2 plus, and 10 will oxidize to Sn3 plus. And let's write the equation. Forward reaction for iron Fe3 plus backward reaction for Sn2 plus Sn4 plus 2 electrons. First of all, make sure the electrons are same in both equations, so we will multiply this by 2 and cancel out the electrons. So this would become 2 Fe3 plus Sn2 plus gives 2 Fe hexachorion ions are pale violet. They form a colorless complex with fluorine ions. Equilibrium 1, and a deep red complex with ioguanate ions. Equilibrium 2. Okay. Predict and explain the sequence of color changes you would observe in each of the following experiments. A few drops of KSCN are added to 5 centimeter cube of Fe3 plus aqueous, followed by a few drops of KF. Okay. So we can see that K stab for H2O5 F2 plus is greater than FeH2O5SCN 2 plus, and this is greater than so according to this we know that first this is added, so the color will change from violet to deep red because this is more stable than this, right? So color will change from violet to deep red. And what will happen when few drops of KF would be added, then color would change from deep red to colorless. How? Because we said that K stab of this complex is more stable than this, so obviously color would change. Okay, so deep red to colorless. A few drops of KF aqueous are added to 5 cm cube of Fe3 aqueous, followed by few drops of KSCN. Now, keeping in mind the K stab K stability constant, you are going to see that of course the color, if we are adding KF to this much of iron, then the color from violet will be changed to colorless. But now what? Then we add few drops of KSCN. The color would not change to deep red because we said that this complex is more stable than this one, so color will not change. So we have to write that it will stay colorless. What type of reaction is occurring during the experiments in part 1? Since this part was related to the transition metal complexes, so it definitely is ligand displacement, or you can say ligand substitution reaction. But ligand should be there. That's it for this paper.